Hey everyone, it's Mr. Ference. We are going to start our next unit today where we're looking at kinematics in 2 dimensions. This first video, we are just going to look at the math of sort of how all of this works. And then in the second video, we're going to take that math and we're going to apply it to studying motion and bring in our kinematics equations again. So to start off, what we've done so far, this first unit, we've just been looking at motion in one single direction or dimension. So it's either going forward or backward. It's either going up or down. But what we're going to be looking at now is where we have things that are maybe going like up and to the right at the same time. That gets a little mathematically trickier. So let's look at just sort of how we can think about this. If we have a jet that's flying through the air at 1,000 kilometers an hour, and it's flying straight into a headwind blowing the opposite direction at 100 kilometers an hour, what is its net total velocity? It's 900, right? Because it's 1,000 going this way plus 100 going this way. Basically 1,000 minus 100. So we get 900 kilometers an hour. You can probably do this in your head, but when we're looking at more complicated stuff, it's going to be helpful to come up with a system of how we can sort of work this out. One of the best systems is actually just drawing a bunch of arrows. So here's our picture for this. We have 1,000 kilometers going this way. We have 100 kilometers going this way. And that gives us a total, what we call a resultant of 900 kilometers an hour in this direction. Again, that's pretty simple just because everything is moving either forward or backward. But what we'll see is when we have things moving in 2 directions at the same time, we can still use this system of arrows and stuff, but it gets a little trickier. So now I want you to think about what happens if we have a jet that is flying that's flying east at 400 kilometers an hour. And there's a wind that is blowing 300 kilometers an hour to the north. Okay, what's actually going to happen is it's going to be like the plane is sort of going to the northeast. And if we want to figure out what its velocity is, it's not 700 and it's not 100. What actually happens if we get it going this way and we get it going this way, we can figure out what that resultant velocity is by using the Pythagorean theorem. Because check this out. If we draw our arrows and we get this set up, so we have 400 going east and 300 going north, this is basically a right triangle. And so if we're trying to figure out a resultant, that's the hypotenuse of this triangle. We can use the Pythagorean theorem, so we plug in 300 and 400, and we end up getting our answer that this is going to be going 500 kilometers an hour to the northeast. So yes, we will be using the Pythagorean theorem because it's really useful. What we're doing here is working with these things called vectors. And I mentioned this last unit briefly, where we have all of our measurements, all of our quantities fall into one of 2 categories. Either they are scalars or they are vectors. Scalars are things that have magnitude. They have a number, but they don't have any direction. So there's no direction associated with your mass. It's just your mass or time or temperature or speed. But vectors have a direction. It's really important to state whether they're going east or west or north or up or down, right? So when we were doing like negative 9.8 because it's going down, that's a vector. The reason it's negative is because it's going down. So we will use positive and negative signs to describe the direction of these vectors. So we can represent these actually as arrows. We just draw the arrow going in the same direction as a vector. So if you have acceleration for gravity, 9.8 meters per second going down towards the center of the Earth, you can just draw an arrow for your acceleration vector pointing straight down. The length of the arrow is going to match the magnitude or the number of the vector. So a faster velocity would have a longer arrow than a slower velocity. When we have vectors that are going off not along just the x-axis or the y-axis, if they're kind of going diagonally, we can actually break them up into what we call components. So if this vector is going off diagonally, it's not just going along the x-axis or the y-axis, we can actually look at just what is it doing in the x direction and what is it doing in the y direction. And so we would call this the x component and the y component of these vectors. We set these components, generally they go along the x-axis and the y-axis, so they're perpendicular to each other. They're at a right angle to each other. The reason we want to do this is because if we have more than one vector, we can actually add all of its x components together and all of its y components together separately to try and figure out what the resultant is going to be, and then we can just use that Pythagorean theorem to bring it back together. Let me give you an example of how this is going to work. I think it might make more sense if you see it in action. Let's say that we have a delivery truck. All right, I'm going to sketch out sort of a thing. It's going 18 blocks north. I'll say north is up. Okay, so it travels for 18 blocks north. It travels 10 blocks east. And then it travels another 16 blocks south. What we're trying to do is figure out what its displacement is going to be from where it started. So not the total distance that it traveled, that would be 18 plus 10 plus 16. But actually, how far is it from where it started, right? What's the distance between its starting point and its end point? What is this displacement here? So here's how we figure that out. The first thing we're going to do is we're going to look at what its motion was just in the north and south direction. Ignore the east and west for now. What was its motion just in the north-south direction? How far is it from where it ended up? And the way we do that is we say plus 18 minus 16. Or if you want to think about it another way, 18 plus a negative 16. Either way, what that tells us is that in terms of just north and south, we are a total of 2 blocks north of where we started. Then we're going to look at how far we are in terms of east and west. This one's a little easier because there's only one motion in that direction. So I'm not paying attention to north and south. I'm just looking at east and west. And that tells us that we are 10 blocks east of where we started. So what we're doing is, right, we're sort of just breaking it into things moving along the, in the x direction and moving in the y direction. We've basically set up this right triangle here. So one side is 2 and the other one's 10. And we want to figure out what this hypotenuse is, right? This displacement, let's just call it d. What we can do by using the Pythagorean theorem is that we say that this is basically all of the x motion plus all of the y motion, the x motion squared plus the y motion squared. We take the square root of that. Keep in mind, this is not simplifying to just x plus y. That's not how math works. We cannot simplify it like that. We just have to keep everything as is and do the square root of that. So that's going to be the square root of 10 squared plus 2 squared. It's not 10 plus 2. If you do that, you will get the wrong answer. If we put everything into the calculator, we end up getting that this total displacement is 10.1 blocks, 10.2, got to make sure I'm rounding correctly, 10.2 blocks from where we started. So that's how we do this, all right? We break it up into the x motion and the y motion separately. We can add up all the x's, add up all the y's, we do the Pythagorean theorem, and we end up with the final answer. So that's how we work with vectors. What we're going to do in the next video is we're going to then see how that affects how we use our kinematics equations. So now we're going to look at using kinematics equations, those same 4 equations, but now we're looking at it in the x direction and the y direction at the same time. I'm really excited for it, and I will see you there. Bye.